Thank you. Okay, well, before I get started, let me thank my friend and former colleague Bob Eisenstein, who used to be on the faculty of University of Illinois, who invited me to come here, and thank some of my old friends and some newer friends for coming, and thank all of you for coming. Okay, so baseball and physics, an intersection of passions. So I've been doing physics all of my professional life. I've been interested in baseball even longer, and about a dozen or so years ago, I figured out how I could, work on baseball and actually call it doing work, okay? So it really is an intersection of passions for me. I want to just point out a couple of things in these pictures. This is a very remarkable picture taken by the Champaign News-Gazette, our hometown newspaper, from a high school game. This is about 7 years ago or so. It's remarkable because you see the ball and the bat in contact with each other. That is a real photo of opportunity. And you can learn a lot by looking at this. You can see that ball is really squished, and it's sort of wrapping itself around the bat. That plays an important role in describing the ball and the bat collision. This picture here is actually a computer rendition of an experiment that was done by a bunch of people, experimenters from Brown University, who used high-speed motion analysis to looking at reflective markers on the ball and the bat to track the incoming ball. Here is the pitch ball coming in at 60 miles an hour. And I think these frames are about every 4 thousandths of a second or so. And here is the trajectory of the bat. It starts out here. The red dot shows you the trajectory of the tip of the bat. And you can see the speed of the bat getting faster and faster, the distance between those red dots getting bigger and bigger as the batter accelerates the bat. And here's the moment of contact. And here is the outgoing ball. Notice that the spacing between the images and the outgoing ball is greater than in the incoming ball. The batted ball speed's higher than the pitch ball speed. And that's what you like to have happen if you're the batter. It's not what you like to have happen if you're the pitcher. Notice also, and I'll talk about this a little bit more, look at the spacing between the images of the bat both before and after the collision. They get smaller after the collision. The bat slows down. And that's a necessary consequence of momentum conservation. The bat transferred momentum to the ball, so the ball had to transfer negative momentum to the bat in order that momentum is conserved. It's like when you fire a rifle, there's a recoil. This is sort of a recoil, but since the bat is moving, it doesn't actually recoil backwards, it just slows down a little bit. Okay, so this is me in my younger days. Is this heaven? No, and the answer is, it's Iowa. In fact, this is Iowa. This is Dyersville, Iowa, home of the Field of Dreams. And this is a picture that my wife took of me pitching at the Field of Dreams many years ago. I don't play quite as much now. I just sort of watch and enjoy. And lately, not including this year, there's been quite a bit to enjoy. All right. So before I go on, let me tell you sort of how I got started learning about the physics of baseball. It was reading this book. Whoops. This book is now in its 3rd edition. I read initially the 1st edition. This is Bob Adair, who has a career sort of similar to my own. Was an elementary particle physicist from Yale, who had, through an interesting connection that I won't go into, became the physicist to the National League. And an outgrowth of that was writing this book. This is a beautifully written book. If you want to read a book that's written by a physicist for general consumption, okay, not for physics, people at various levels can get a lot out of this book. I, as a physicist, got a lot out of this book. But just people who are fans of the game who don't really know a lot of physics can get a lot out of reading this book. And I highly, highly recommend it. It's a brilliantly written book. Okay. Our goal, this is important, our goal is not to reform the game, but to understand it. Many times people ask me, I think there was a radio interview with me that I actually did 2 days ago, but it was broadcast today, and they asked me this question, did Major League Baseball players ever benefit from anything that I do? And the answer is no. They already know how to play that game. The game has been evolving for 150 years, so they know from however, trial and error or whatever, how to play the game. The goal of a physicist is really to try to understand what they, put on a sound physics basis what they already intuitively understand. So when you ask a ball player what they do, they know what to do. They may not give you the right reason for it, okay? In fact, they oftentimes do not. I'll try to give you the right reasons, okay? But they certainly know what to do. Okay, so topics I'll discover. I'm going to talk sort of generically about 3 different things. The ball-bat collision, how a bat works, and I'll get in talking about the differences between wood and aluminum bats, since that's sort of a hot topic. It's been a hot topic for years. I want to talk about the flight of the baseball, air resistance, the so-called Magnus force on a spinning baseball, and all that sort of stuff. And then towards the end of the talk, I'm going to really switch away from talking about pure science and talk about new tools that are actually revolutionizing our ability to analyze the game of baseball, not from a science point of view, but from a baseball point of view. New tools for baseball analysis. And so that'll be kind of fun, I hope. We'll see. All right, so now I have to step back here because to get these videos started requires manual intervention. I want you to watch these videos here. Now I'm out of the way and you can see them. So here's a baseball being projected onto a steel plate at high speed, and it's supposed to be bouncing off. And why isn't it? I don't know. Let me hit it again. Say again? Yeah. Let me get out of the way. Okay, there it's bouncing off. Watch this collision. Notice how the bat slows down. I told you about that already. Watch it the next time around. Watch the bat slow down after it meets the ball. Just hit the left button there. Hopefully that'll, all right. Move the cursor on the lower. Yeah, there you go. Now hit the left button. All right, now watch the bat slow down. So, so let me talk while you're watching. So the ball-bat collision is, for me, one of the most fascinating parts of the game, okay, from a science point of view. When the ball hits the bat, it's a very violent collision. The forces between the ball and the bat are large, like 8,000 pounds or more on average, but they last only for a very short amount of time. But less than 1,000th of a second. During that time, the ball gets crushed. You saw that in the still picture. You couldn't quite see it on this because it's not a fast enough photography. But the ball really gets compressed to maybe half its natural radius, comes to a momentary halt. If it's going this way and it's got to go that way, it's got to stop first. So it comes to a stop, and then it pushes back out against the bat. So if you think of the ball as being sort of like a spring that you can compress, the initial energy of motion, the kinetic energy of the ball, gets converted into the potential energy, that's the PE part here, of a spring being compressed, and then goes back into kinetic energy again. And the bat recoils backwards. Well, as I said, it doesn't really recoil backwards because it's already moving forward, but it just slows down. So the bat transfers forward momentum to the ball, so the ball has to transfer backward momentum to the bat. This is a very, very inefficient process. A lot of energy gets lost in the process. And to appreciate the ball-bat collision, you have to appreciate that fact. And most of the energy gets lost due to the distortion of the ball. Some of it gets lost, and we'll get into this a little bit later, due to vibrations in the bat. We know about vibrations in the bat when the bat stings, but we'll get to that in a little bit. Okay, so let me move on. First of all, let's see, is this where I want to be? Yes. For the batter, probably the most important aspect of the collision is the batted ball speed. The batter's goal, among various goals, but the principal goal is to hit the ball as hard as possible, meaning the ball is going to come off the bat as fast as possible. You want a high batted ball speed. Obviously, that's true if you're trying to hit a home run, okay? But even if you're just trying to punch the ball through the infield, except for certain situations where you're bunting or something like that. But most situations, you know, the faster that ball comes off the bat, the less likely a fielder is going to catch up with it. All right, so then the obvious question comes up, what determines the batted ball speed? Okay, well, the only equation you're going to see in this talk is right here. And this is a very simple equation. Batted ball speed, BBS, is equal to some number, Q. It's a property of the ball and the bat. I'm going to call it the collision efficiency. It characterizes how efficient that collision is. Q times the pitch ball speed plus 1 plus Q times the bat speed. Okay, so this is the only equation you're going to see. But let me give you some typical numbers, though. I won't tell you how I arrived at these numbers, but these are typical numbers for a ball hitting the bat, you know, at the sweet spot of the bat, somewhere near the fat, where's my bat? In the fat part of the bat, a few inches in from the end, maybe 4 or 5 inches in from the end. A head-on collision. That number is about 0.2. By the way, this demonstrates how inefficient that collision is. If the ball were a super ball and the bat were infinitely heavy, that number would be 1. And so it's only 20% of 1. Okay, so that sort of characterizes how inefficient that collision actually is. It's only 0.2. So put in some numbers. A typical good fastball, 85 miles per hour. Wait, you say a good fastball is not 85 miles per hour, it's 95 miles per hour. Yes, when it leaves the pitcher's hand, it's 95 miles per hour, but when it crosses home plate, it's 85 miles an hour, and that's what matters. 70 miles per hour is a good swing speed. Put those numbers into this equation, you get 101 miles an hour. And a 101 mile per hour ball hit at you know, sort of the optimum angle with a lot of backspin on it, and the optimum angle is about, I'll get into that a little later too, is about 30 degrees. That ball will carry about 400 feet. That's a home run in most ballparks. The canonical 400-foot home run. Okay, so now, the thing that you may not have appreciated by just looking at this equation is, notice that this number, 1 plus q, is 1.2, and the q is 0.2. That means that bat speed matters much, much more than pitch speed in determining how fast that ball is going to come off the bat. Each additional mile per hour of bat speed is worth about another 6 feet on this 400-foot home run. Each mile per hour of pitch speed is worth maybe 1 foot. It's a factor of 6 different. So anyone who's ever played the game really knows that, okay? You may not have realized how big an asymmetry it actually is. So for example, you can hit a ball off a tee, in which case the pitch speed is 0, and you know you can hit that ball a long ways. But then try bunting the ball where the bat speed is 0, and it's all pitch speed, and you know the ball's not going to go very far. So you sort of intuitively knew this already, and you may not have realized how big an asymmetry it really is, though. Okay, so now, working our way through this, so this tells you how the collision of how the batted ball speed depends on the pitch speed, the bat speed, and this number q, this collision efficiency. Now the question is, what does q depend on? We want to figure out what properties of the ball and bat that this q depends on. And so I'm going to talk about 3 specific properties. Okay, the weight of the bat in the barrel. Okay, so here's a bat. Now, so again, everyone, you know intuitively, you can hit a ball harder with something heavy than you can with something light, right? You sort of know that. But what you may not realize is that it's, let's see if I have it. Oh yeah, well, let me back up a second. So the heavier the bat is, the larger this Q is, okay? The larger this collision efficiency is. So again, you know, you take a broomstick and try to hit a ball with a broomstick. You're not going to be able to hit it very well. You want something more massive. And the reason why is quite simple. Remember, when the ball hits the bat, if the bat were initially at rest, it would recoil backwards. That's energy that might have gone into the ball, but instead went to the bat. And the heavier the bat is, the less it's going to recoil. And that's really all there is to that. Now, of course, there's an interesting trade-off because you have to swing the bat also, right? Okay? So whereas Q is larger, this collision efficiency is larger for a heavier bat, you're not, a typical bat is not going to be able to swing a heavier bat as fast. So you can see there's a trade-off here, and you can sort of ask then, what's the optimum weight of a bat for a batter? That's a question people oftentimes ask. What's the ideal bat weight? Well, when trying to approach this from a physics point of view, part of the problem is easy and part of the problem is hard. The effect of the bat weight on this collision efficiency is easy. That's just, you know, a simple calculation you can do. The effect of the bat weight on the bat speed is much harder. In fact, that's likely to be quite an individual property, individual to a given batter. Nevertheless, people do experiments and are able to more or less characterize how a typical batter's bat speed depends on the weight of the bat. Bat speed depends on the weight of the bat. In fact, that very first slide where I showed you the computer rendition of the bat and the ball being tracked, that was probably the best experiment of that type that's been done. Because in that experiment, batters used bats of different weight. Now, for the people who are really, who want more technical information, it says here the weight of the bat in the barrel. In fact, what really matters is the property of the bat, which is called the moment of inertia of the bat, about the handle. But it's related to how heavy the bat is, but also where that weight is along the length of the bat. And it's really the weight of the bat in the barrel that matters. So one interesting question that comes up from time to time is, what about corking a bat? Okay, this is something that is an illegal act, okay? So what is corking the bat? Well, this is going to show you what corking the bat is. So in June of 2003, I woke up to learn that Sammy Sosa, the former great slugger for the Cubs, broke his bat, and here it is, and out popped this cork, okay? And all right, and then this totally dominated the sports news for 3 or 4 days, and my phone didn't stop ringing for probably 2 days. One reporter after another was asking me about this. So what do you do? What's a cork bat? This sort of shows you here. The idea is the following. You take a wooden bat and you drill a hole about 1 inch in diameter and about 10 inches deep into the bat, making a cavity, and that makes the bat lighter. Lighter bat is going to give you a higher swing speed, but a lower collision efficiency. Okay, it's a trade-off. You fill it with cork. The cork itself does nothing other than disguise the fact that you've done this illegal act. You backfill it with a very light material, and then you just paint over it so the umpire doesn't know. So the question is, well, how does this trade-off work? You get a higher swing speed, but lower collision efficiency. So when I went through a careful analysis of this, I concluded that if your goal in life is to, hit the ball as hard as possible, to get the longest home run as possible, it's a losing proposition. Okay? And for a few months after this incident occurred, I give talks fairly regularly on this stuff, and the title of my standard talk at that point was, "Did Sammy Sosa take Physics 101?" And it's clear that he didn't, because if he did, he would have known this. Now, that's not to say that cork bats are not without value. In fact, you may not hit the ball harder, but what you may well do is hit the ball well more frequently. Because with a lighter bat, even though the collision efficiency is not as high, that bat is more maneuverable. You can wait a little bit longer on the pitch before you decide to swing. You can adjust more easily the swing once you've started the swing. So if you're a singles hitter, a guy who punches the ball through the infield, maybe hits a gapper or two, from time to time, a cork bat actually can help you. But if your goal is to hit home runs, my conclusion is that it doesn't. Okay, second question. Second point, what does the collision efficiency depend on? It depends on the bounciness of the ball. And the bounciness of the ball has a technical name. It's called the coefficient of restitution. And so let me just show you. Here's a super ball here. Maybe you could just turn the light on for a second. You could bounce, here's a super ball. If I drop this super ball, this is not a great surface, but usually it bounces very close to its initial height, which is another way of saying that no energy is lost when that ball hits this hard surface. So the coefficient of restitution is 1. Do this with a baseball, and look what you get. It hardly bounces at all. I mean, if I were to do this more carefully on a really good surface, it would probably bounce to about 1/4 of its initial height, which is to say that the coefficient of restitution is actually the square root of 1/4 or 1/2. So the coefficient of restitution for a baseball is about 1/2. But that 1/2 means since it only bounces to 1/4 of its initial height, 3/4 of the energy is lost. And that's a large part of the reason why the collision efficiency is as small as it is. Okay, you can turn the lights off now. So here I've shown you in this slide here, bouncing various balls. Here's the initial height, and here is a steel ball on a steel plate. It's got a coefficient of restitution of very close to 1. A super ball is a little bit less than that, and a baseball is over here somewhere. So different balls have different coefficients of restitution. So that bounciness of the ball plays a big role in that collision efficiency, and therefore what happens during the ball-bat collision. Okay. Before I get the video started, or I guess one of them started already, put the cursor on the left one and then hit the left button. This is the ball. You've already seen this one before. This is, oh, don't end the show. Ah. Yeah, I'll get it. Yeah, I know. I'll put you at a disadvantage here. Is that going?
This one's going.
Okay, now watch this one. This is hitting the sweet spot. Now, what I want you to do is watch what happens to the bat after contact. Watch very carefully. Watch his hands especially. You see? That hurt. Now, okay, so the ball hit on the sweet spot of the bat here. It hit outside of the sweet spot. Here I have another one which I won't show you where you hit inside the sweet spot. When the ball doesn't hit the bat at the right spot, the bat vibrates, it hurts, you know that, you feel that, it's not a pleasant feel. But more to the point, as far as the ball-bat collision is concerned, the bat starts to vibrate, and that's energy that might have gone back to the ball, but instead got transferred to the bat in the form of vibrations, which again lowers that collision efficiency. So the best place to hit the ball, the best place along the bat to hit the ball is where those vibrations are the smallest, the sweet spot. And you can take any old arbitrary bat, and here's any old arbitrary bat. This is about as any old and arbitrary as you can get. It's a little league bat, 27 inches long. You know, major leaguers are using 33 or 34-inch bats, and 19 ounces, okay, very light. Okay, so you actually can hear the vibrations. And you can feel them. So I'm holding the bat very lightly, maybe 5 or 6 inches in from the knob. And now you can start to work your way. Hear that? It sounds very different when I hit it right here. I'm hearing maybe a little bit higher frequency vibrations, but the lowest frequency vibration I'm not hearing. And that's, you know, that's a so-called node of the vibration, and that is basically where the sweet spot is. And that is, you know, that's probably the best place for you to hit, for the ball to hit the bat. Yes?
Is the barrel linear in weight?
No, the barrel...
Is the end lighter than the middle where the sweet spot? I was just saying, is the weight of the whole barrel linear?
It's not uniform because this one, you could even, well, I mean, it depends on the bat. Many bats have, depends where the taper starts. I mean, here there's sort of a uniform region which is maybe 4 inches long, and then it starts to taper pretty quickly. And where that sweet spot is depends on the details of those shapes, of course. So it's different for different bats, but for almost all bats, that sweet spot is somewhere between roughly 5 and 6 inches in from the barrel end of the bat. Okay, now what's coming up here? All right, so now, does aluminum outperform wood? What's different about an aluminum bat? So in professional baseball, they're required to use wood bats. In virtually every other level of play, whether it's college or high school or Little League or Babe Ruth League or any of those, they can use non-wood bats. And what's different about a non-wood bat? This is a non-wood bat, by the way. This is an aluminum bat. Okay, so whereas a wood bat is a solid object, okay, an aluminum bat is a thin shell. This is a very thin, maybe 0.15 or 0.13 inches thick. It's a thin shell. If you open it up, it's hollow. You could, you know, you could put your lunch in there or something, I don't know. But it's a very thin shell. So this sort of gets partly to your question. For a wood bat, okay, a larger fraction of the weight of the bat is in the barrel because the barrel is a solid piece of wood. Whereas for an aluminum bat, a smaller fraction of the total weight of the bat is in the barrel. Or said more technically, the moment of inertia of that aluminum bat is less than for a typical wood bat, for a wood bat of the same length and the same weight. So an aluminum bat is going to be easier to swing, but it's going to have a lower collision efficiency just considering the weight aspect of it, just considering the distribution of weight. So there's no net advantage from the point of view of batted ball speed because of that different weight distribution. It's like the corked bat argument. So what is the advantage of an aluminum bat? Well, the real advantage of aluminum bat is the fact that when the baseball hits a wood bat, it's hitting essentially a rigid surface. I mean, the bat can vibrate a little, but it certainly can't compress very well. So essentially, all of the energy of the ball goes into compressing the ball, and that's the thing that's a very, very inefficient process. But when the ball hits this thin-walled aluminum bat, I can sort of show you with this water bottle here, the wall of the bat itself can compress. So some of the energy goes into compressing the bat, and that energy is very efficiently returned back to the ball again. And so you get a bigger bounce when the ball hits an aluminum bat. The coefficient of restitution, if you like, is larger. So you can actually have when the ball hits an aluminum bat, the coefficient of restitution of the ball is larger than when it hits just a steel plate. So it's that extra bounce that makes the aluminum bat much better than the wood bat. And I have really cute little demo of that. For this, I guess I would like the light on. Okay. I have two balls that look virtually identical. This is really cute. And I don't even know which one is which myself until I bounce it. One of them is totally dead. This one is totally dead. I hit it, and it thud. Coefficient of restitution, 0. This one is sort of a super ball. And these things look virtually identical. Happy ball, sad ball, I call them. Okay. So when I bounce that off of a hard, rigid surface that can't compress, one of them bounces very well, the other doesn't bounce at all. Now I want to bounce it from my little bongo paddle here. This is my aluminum bat. This is my wood bat. My aluminum bat, this is an aluminum bat on steroids in some sense, taken to an extreme, where this is now a very, very thin membrane. Now watch what happens. Now I'll mix the balls up. I don't even know which one is which. Bounces pretty well. Bounces pretty well. They both bounce more or less the same when bouncing from this surface. And the reason is that almost all of because this surface is so much more flexible than the ball itself, all the energy went into compressing this surface. None of it went into compressing the ball, and all the inefficiency comes from the ball, and so you just got a bigger bounce. So this is, in the lingo, this is what is known as a trampoline effect. You can imagine jumping on the floor, you can't bounce very high, versus jumping on a trampoline where you could really bounce quite high. And that's a trampoline effect, and that is the principal reason you can kill the lights now, why aluminum outperforms wood. Okay, additional remarks on this collision efficiency. It can be measured in the lab. And so one of the things that I do is I'm sort of an advisor to the NCAA. Anybody play NCAA baseball or know anything about NCAA baseball or follow it? If you look at the newspapers, you'll see that, well, the NCAA has been regulating the performance of non-wood bats for a decade or so now, but they actually just changed this year to a new technique for doing it. It's a technique, actually, I'm proud to say that I was the one who authored. And it actually has had a dramatic effect on on offensive statistics in Major League Baseball. So the bats used in NCAA play today, and those same bats will be used nationally in high school baseball beginning next year, reduce dramatically the number of home runs, number of runs. And what they're doing is essentially regulating away this trampoline effect. They're essentially saying that when you bounce the ball off a wood bat and you bounce the ball off an aluminum bat, that coefficient of restitution can't be very different from each other. So the bats perform like wood. And so thus far, I think the statistics I've seen, home runs are down something like 35% this year over last year. There's lots of articles written about it. Okay, here's one more thing before I move on to talk about other things. And this is cute. This is, so, you know, when you start doing calculations, and you can test those calculations, but we're doing experiments, and you can actually learn a lot of things, and you could develop models for the bat. And the models, once you're happy that you can reproduce experimental data, then you can start looking at things in your model, in your calculation, that you can't easily do an experiment on. So one of the very first things that I did when starting to look at principally wood bats, but it applies just as well to aluminum, is that the hands don't matter. And what do I mean by that? So when the ball and the bat, during that brief instant of time, 1,000th of a second, when they're in contact with each other, the fact that the batter is holding the bat, assuming that he's holding it near the handle and the collision is out here, doesn't matter at all, okay? Now, most people don't believe that, okay? In fact, it's somewhat non-intuitive to a physicist, it's actually fairly simple to explain. But let me give you the fact first, and then I'll give you the sort of the technical reason why that's the case. The fact is that just prior to the bat hitting the ball, the batter could just as well let go of the bat, and it would not make any difference as to what happens to the ball. Nothing, no difference whatsoever. The batter does not muscle the ball while the ball and the batter are in contact. Once that bat is up to speed and in the right place at the right time, the batter plays absolutely no role whatsoever. It really is true. Now, and the reason why is the following. It's because the collision time, so what happens, the ball hits the bat out here, and the bat actually deforms, and a little wave ripples down the end of the bat, and it bounces off the end of the bat and comes back to the beginning again. And the time it takes the ball, the wave to go down the end of the bat and back again, by the time it's back again, the ball has already left the bat. So literally the ball doesn't know anything about the other end of the bat. You could chop the knob off, or it doesn't matter how it's supported or anything. Okay, that's kind of cute, and I like to always tell people about that. Okay, now I'm going to switch gears a little bit and talk about forces on a spinning baseball in flight. So here's the magic of PowerPoint. You see a ball spinning. It's traveling through the air. This is its velocity. It's traveling through the air like this. Okay, so let's talk about the three forces that affect the trajectory of that ball. There is the weight of the ball, mg, the weight, okay? And that's straight down. That acts vertically downward. It's pulling the ball, pulling everything back. What goes up must come down, okay? There is the air drag, or air resistance, or sometimes people call it wind resistance. It's the fact that the ball has to push the air out of the way. If the ball were traveling in a vacuum, there would be no air resistance. The ball would travel a heck of a lot further. But there is air resistance, whoops. And the drag slows the ball down. The drag acts in a direction directly opposite to wherever the ball is, whatever direction the ball is going. The ball is changing direction, so the drag force is also changing directions. Then there's the Magnus force. I'll talk a lot about the Magnus force. The Magnus force is the force on a spinning baseball. It's the force that makes the curveball curve, okay? And if you want to know the direction of the Magnus force, the easiest mnemonic, the easiest way I have to explain it to people, you know, you can go through, and if you're in a physics class, you have all these right-hand rules, but you don't have to do that. What you do is you look at the leading edge of the ball. Here's the front edge of the ball. The ball's headed this way, and you look at the direction that the front edge of the ball is turning, and that's the direction of the Magnus force. So this ball, the front edge of the ball, because it's spinning like this, it has backspin on it, it's pointing just in this direction. So the Magnus force acts perpendicular to the velocity, and it's upward and sort of backward. Okay? So the drag serves to slow the ball down. The Magnus force and gravity both tend to deflect the ball from its straight line trajectory. So both of these contribute to the fact that the ball doesn't travel in a straight line. So how important are these forces? Barry Bonds, who was found guilty on one count just today, and the other, breaking news, Barry Bonds found guilty on one count, and 4 other counts, there are a hung jury, yes. Okay, when he hit his 756th home run, the one that broke Hank Aaron's record for career home runs, back in 2007, August 7th, I believe, okay, I actually managed to get hold of data for tracking the ball. And what I got hold of is data on the initial part of the trajectory down here. That's the red stuff. And I got data on where the ball landed and how long it took to get there. And that's completely sufficient to determine the full trajectory of the ball. You see, if the ball hadn't hit something, it would have gone a little bit further and it landed about 430 or so, 435 feet from home plate. Okay, so this is a full aerodynamics calculation with all the effects of drag and the Magnus force in it. Okay, so now what you can do is, all right, now let me go through the same calculation again with the same initial conditions, but now let me pretend it took place in a vacuum. No drag, no Magnus force. Where would that ball end up? It would have ended up close to 700 feet from home plate. So when we tell people in our introductory physics courses, calculate the trajectory of a ball going through the air, ignoring the effects of air, it's a bad approximation. For a baseball, it's a very bad approximation. Now, if you turn on the air drag, the air resistance, but don't turn on the Magnus force, you get this trajectory here, okay? So now you turn the Magnus force back on again, and you get that there. So what happens, the Magnus force, this ball had backspin on it, okay? So if a ball is going off like this, the principal direction of the force is up. So if the ball is taken off at a fairly low trajectory, this was a 27-degree initial angle, the Magnus force keeps that ball in the air longer, so it'll travel farther. So in this case, the Magnus force actually gave him an extra 40 or 50 feet or so on that home run. But this sort of goes to show you what the size of those effects are. The Magnus effect on a golf ball is even, you can get a lot of backspin on a golf ball. And if you look at a good tee shot with a lot of backspin on it, the optimum angle for the initial angle is, you know, in a vacuum is 45 degrees. It's a very low angle. And you see that ball take off, and you could see it rise before your eyes. I actually have a light ball. I was going to throw it, but you're, you know, I can make this ball curve. So let me put a little bit of side spin on it, so it'll swerve that way, hopefully. It didn't. Let me do it again. Let me try it again. All right, heads up. No, didn't again. I didn't rehearse this. But if you have a light enough ball, you could easily get enough spin on it to make it curve like that. You could do it with a ping pong ball especially. Okay, so that's what the size of these effects are. So now I want to sort of switch gears just a little bit and talk about new tools.
So may I ask a question?
Yeah.
Where does the backspin come from?
Where does, I want to get to that. How does the batter put backspin? I'll get to that, yeah. The question was, where does the backspin come from? How does the batter put backspin on the ball? And that's the question I'll get to. Okay. All right, so I'm going to talk about, well, the two principal things I'm going to talk about are the so-called PitchFX and HitFX systems. It was the PitchFX system that allowed me to track that Barry Bonds home run. In fact, this is Barry Bonds, and this is the ball in two different frames here. So what is the PitchFX system? Those of you who watch baseball on TV have actually seen it and may not have known you've seen it, but you've seen it. There are two video cameras permanently installed in every major league ballpark for the last 4 or 5 years now. Typically, one is high above home plate looking down, one on the first base side. This is the first base side. Every pitched ball in every major league game is tracked. So with two cameras, you look, you know, each camera, so if you look at where the image of the ball is in this camera, it determines, well, all you really know is from a single camera is a line, but you have a second camera, and you look for the intersection of those two lines, and that tells you in three-dimensional space where the ball is. And so from that, you get a smooth trajectory. And you can use the same cameras to track the initial trajectory of the batted ball, and that's what I've shown you over here, but just the initial part of that trajectory. This is Marv White, who actually was an undergraduate physics major at the University of Illinois, but long before I got there, who was the chief technology officer of this company that developed all this. This is used for analysis. It's used for TV broadcast, MLB Game Day. So here's a TV broadcast. This is a Fox broadcast. They show you this little rectangle off to the side, which is the strike zone, and they show you where the ball ended up relative to the strike zone. That comes from this pitch tracking system. They tell you, you can't read this too carefully, but it tells you how much break there was in the ball, the speed of the ball being different, as I told you before, when it's released than when it crosses home plate. It loses about 10% of its speed just in those 55 feet or so. Those of you who sneak around at work when you're supposed to be working, watching MLB Game Day, you know, you see stuff like this, and you see, they tell you, nowadays they even identify what kind of pitch was thrown based on information that I'll tell you about in a second. So this has provided, if I didn't say so already, yeah, here it is here. All the data for this are publicly available. Anyone here can go and download the data and just analyze it to their heart's content. Thousands and thousands and thousands of pitches. And people do that. People do that. And people have learned a lot about the game of baseball by doing such things. And a lot of the people who started out just writing blogs, online, are now working for major league teams. hired as the analyst doing just this sort of stuff. Okay, so let me tell you a little bit more. Using HitFX to discover how pitches do what they do. Ted Williams said hitting is 50% above the shoulders, you know, thinking. And Warren Spahn said, there it is, hitting is timing, pitching is upsetting timing. And by the way, Jerry, these are cards from the 1955 Topps cards from my personal collection. This is my favorite set of cards. All right. Yeah. I'm going to skip this. Okay, so I want to give you a few examples. Mariano Rivera is the great closer for the New York Yankees. He's, what, 43 or 44 years old now. He hasn't slowed down a bit. I mean, he's been doing this for years. The greatest closer. So he's a guy that comes in with a lead in the ninth inning and shuts him down. Why is he as good as he is? I'm going to tell you, as with real estate, there are three reasons. Location, location, location. So this is every pitch thrown by Mariano Rivera for the 2007 through 9 seasons, I think it is. And this is the location of the pitch as measured quite precisely to roughly an inch by this system. The center of home plate is here. Here are the edges of home plate. And you look where he throws these pitches. I mean, this guy lives on the paint, as they say. Okay, he's in the black. You know, the home plate is white and the little rim around it, that's what they call the paint. That's the black part of home plate. So he does not give batters anything good to hit. Compare that with the location of pitch baseballs for every home run hit during that period. It's right here. And I've superimposed it. So here's Mariano Rivera. Here are home runs. So, you know, he stays away from the center of the plate. And he does it consistently. So that's one of the reasons why he's as good as he is.
Which of those things would have been called strikes?
Ooh, that's a good question. There's a bit of fuzziness to the boundary. In fact, this is one of the problems people are working on, is to try to study umpires' trends using this system, calibrate umpires. Okay, he gets a lot of close calls because he is who he is. Okay, I want to show you something else though. So Mariano Rivera he only throws 2 pitches. He throws what is called a cutter, and he throws a so-called 4-seam fastball. And they do slightly different things. Okay, he's a right-handed pitcher. Typically a fastball has backspin. And so the movement on a so-called 4-seam fastball is upward. The ball doesn't actually rise because gravity's pulling down on it, but it doesn't drop as fast as it would have otherwise. But his cut fastball has a little bit of side spin on it, in addition to the backspin, in such that it breaks in on a left-handed hitter. And so here is a typical pitch of Mariano Rivera, a cut fastball, thrown probably to a left-handed hitter. I actually don't know. Here's home plate. So the scales are very different here. This is 60 feet from home plate. This is home plate, okay? And this is the horizontal position. You're looking at an overhead shot. Here is the actual trajectory of the ball, the red trajectory here. It almost looks like a straight line, but it's not quite a straight line. In fact, this dash thing is a straight line. So if a batter looked at this pitch, okay, over the first 30 feet of that, the batter would have concluded, you know, it's indistinguishable from a straight line trajectory, and it looks like it's going to end up here. But in fact, it ends up here. Okay, Mariano Rivera breaks a lot of bats. He does. He really, really does. Left-handed hitters, they see that ball, looks like it's going to come over the corner of home plate, and it ends up on their hands. And they hit the ball off the handle, and the bat breaks. And if you thought you had it calibrated, then he'll throw this one. This one had almost no break whatsoever. So this one, you know, less than 1 inch of break. So if you thought, I'm looking at this, I'm going to lay off from this pitch because I think it's this one, but no, it's this one. These pitches are virtually indistinguishable for the first 30 feet of flight. And the first 30 feet of flight is about all the batter has to be able to look at the pitch and decide what to do. Because, you know, you've got to spend the rest of your time, you know, processing the information and getting that bat around. It takes, you know, it probably takes about, on this scale, about 20 feet or so just to get the bat around. So that's another reason why he's as good as he is. He disguises his pitches very, very well. Okay.
What would have happened if it was the old mount? Put it lower the mount? What would that have meant to yours?
Well, his release point would have been different, and he would have had to adjust the initial downward trajectory of the ball. It wouldn't have had an enormous effect for someone like him. It would have taken, so back in after the 1969 season, or was it the 68 season? One of those. They lowered the pitching mound from X inches to 10 inches. Like, what was it, maybe 15 inches to 10 inches. And to remove some of the advantage a pitcher has. And what would that have done? I don't know. People that learn how to adjust, it probably wouldn't have had, it might have had an initial effect, but it wouldn't have had a lasting effect. Because, again, everyone learns how to adjust. So,
Does Rivera know what he's doing?
oh, he knows what he's doing. Yeah, he knows what he's doing. He knows what he's doing. Well, I don't think he looks at data like this, by the way. Maybe he does, but I look at the data. But he knows what he's doing. He knows how to control the pitch. He knows he has another pitch that he throws in which the slight little side spin is in the opposite sense, so it breaks the other way. And he typically throws that to right-handed hitters. And sometimes he throws it to left-handed hitters where the ball looks like it's going to go off here and then it curls back in at the last minute, rides back in. So, but he doesn't throw, he mostly throws that to right-handed hitters, though. And people have analyzed this a lot.
Do the batting coaches do any probability analysis to help the hitters know what kind of hitter you're going to be throwing?
I don't know, I really don't know the answer to that. I suspect that, I doubt that they're looking at data like this. They know intuitively what pitchers throw. You know, they talk about late break. You know, this is an example of late break. From a physics point of view, you know, you can't have a trajectory that kind of goes like this and then takes a sudden turn. That physically is impossible. And so what players mean when they talk about late break, I believe, is exactly this. You know, both of these are perfectly plausible trajectories from a physics point of view, but they look virtually identical, you know, well into the trajectory. Okay, let me move on. So this is kind of cute stuff. This is Jon Lester, a left-handed pitcher for the Red Sox. And what I'm doing is plotting from a catcher's point of view the amount of break in inches on a pitch. So this is the break due to the fact that it's spinning. So gravity is removed from this. Okay? So the deviation from a straight line trajectory, not counting gravity, due to the fact that the ball is spinning. And I show you this plot to show you that there's some regularity to this whole system here. You see that on this plot. So this is from a catcher's point of view. Okay? No break would be right in the center of this plot. So this would break in on a left-handed hitter. This would break away from a left-handed hitter. This would break up. This would break down. And you could classify his pitches with basically three parameters: the horizontal movement, the vertical movement, and I've color-coded the third of these, the speed of the pitch, the release speed. And so there are nice little categories here. A four-seam fastball. Mostly it breaks up. It's got a little bit of side spin that makes it tail in. So players call it arm side break. It breaks in the same direction as the pitcher's arm. Four-seam fastball is sort of the staple of his repertoire. He has a two-seam fastball, and there's another cluster lying right on top of it at a lower speed. So you see there's some red and orange, and then there's some green here. Okay, that is his changeup. And that has less backspin but more side spin on it. So this really tails into a left-handed hitter or away from a right-handed hitter. In fact, probably this two-seam fastball is probably the most important pitch in his repertoire. Sometimes they call this a sinker, not because it's sinking, but because it doesn't rise as much as a four-seam fastball. Okay? This is a curveball. Actually, the easiest pitch to identify is a curveball. It's the only one falling below the line. A curveball is largely thrown with topspin, so it breaks down. And usually glove side it breaks. But it's mostly a downward break. And then this pitch is a slider or a cutter. I'm not sure. I think it's actually a cutter. And they both do similar things, and they're not easily to distinguish from each other. But anyway, people look at these things, these plots, and try to classify what the repertoire of given pitches are. So here's Jon Lester. Here are those 4 clusters. There's 5, but there's one lying underneath this one. Brandon Webb is a well-known sinker ball pitcher who used to play for the Diamondbacks. I can't remember who he plays for now. Maybe some of you know. Compare these two guys. He's a right-handed pitcher, so his curveballs are on the opposite side here, horizontally. So this is his curveball, but look at his fastball. There's virtually no rise to it at all, and you can appreciate how that might be by looking at what you might call his arm slot. He's throwing, he releases the ball almost off to the side, which sort of inhibits the backspin on the ball, but gives you side spin. So he gets a lot of side spin on the ball, but hardly any backspin on it. And so you see there's a huge difference between these two guys, 15-inch difference in the amount of movement on their fastball. So this guy, this guy is doing a good job when people are hitting ground balls. He keeps that ball low. And then there's Tim Wakefield, who's a knuckleball pitcher, and he does have a fastball occasionally and does have a curveball, but it's all over the place. Okay, I'll have a little video, but I'll skip the video. Okay, now learning about batted balls. HitFX uses the same cameras as PitchFX, but it only gets that initial part of the trajectory. So here's an analysis I did a year or so ago. I had about a month worth of HitFX data from the early, actually I did this 2 years ago, from the early part, from April 2009. And what I'm plotting is a quantity that statisticians call the batting average for balls in play. So baseball nerds know what this is, the rest of you don't. I'll tell you what it is in a second. Versus the vertical launch angle, okay? Batting average for balls in play. It's singles, doubles, triples, not home runs, divided by total balls hit, excluding home runs. And the reason why people like to keep track of it is these are balls in play. A home run is not in play, and no one can field it, right? So there is sort of a lore among baseball analysts that this number is typically about 30%, about 0.3, independent of who's pitching, independent of who's batting, and people use that as a measure of how lucky or unlucky you are. So if a pitcher seems to be pitching very well, but his batting average for balls in play is down around 0.2, people think, well, that's probably not sustainable. He's been lucky. Or if it were a batter, you would say the batter's been unlucky. But, you can question whether, how much of this does the pitcher really have under control, how much of it does the batter have under control. So this is batting average versus balls in play for balls hit with an initial batted ball speed of 90 miles an hour, which is a pretty good hit. And you see that if you're hitting the ball at about 10 degrees, over 90 miles an hour, you're going to get on base about 90% of the time. And so what is that ball doing? You're hitting it hard, first of all, and with a 10-degree initial launch angle, that's just enough to get over the infield, but not so high that the outfield can catch up with it. And that's exactly, that's a hitting strategy, okay? Ideally, what you like to do, batters would like to do, is hit such balls with topspin on it. You don't want the ball, if it would backspin, it would stay in the air longer, the outfield can catch up with it. You want to have topspin, like a good topspin return in tennis. It clears the net and takes a nosedive. On the other hand, this is what that plot looks like for home runs. You see, if you want to hit if your goal in life is to hit a home run, you also want to hit it as hard as possible, but you want to hit it, at somewhere between 25 and 35-degree angle. These are very complementary to each other. So the hitting strategy for getting on base is different than the hitting strategy for hitting home runs. I mean, players know that, but this quantifies it. All right, the very last thing I want to, probably the last thing I'll talk about is, no, I'm not going to talk about this. I'm going to skip this. I'll go back. So because somebody asked me a question, and because we went to the trouble to bring this basketball, put the light on just for a second. How does the batter put spin in the ball? So when I talked about that first equation and that collision efficiency, I was talking about head-on collisions. But very rarely is the collision a head-on collision. Sometimes it's an oblique collision. So when the ball, so here's the ball and the floor is my bat. If I hit it head-on, the ball doesn't spin. But if you want to catch this? If I throw it at an angle, watch what happens when it bounces. You see, it bounces with topspin. And how does it do that? Thanks. The reason why it does that is because there is a component of the velocity of the ball that is along the surface of the floor. There's friction, which acts in the opposite direction, and that friction gives you a torque that starts the ball spinning. And that's how a batter puts spin on the ball. It's the friction when you have non-head-on collisions. You can turn the lights off now. Non-head-on collisions, it's the sliding friction of the ball sliding along the surface of the bat that gives you spin. And you can control that spin depending on how you hit the ball. So let me just tell you some familiar results. If you're, so just watch any game and these are just common phenomena that you always see. Balls hit to the left or to the right always break towards the foul line, whether they're hooked by, so if you're a right-handed hitter and you hit it, down the line, it always breaks towards the foul pole, okay? Or if you slice it down the right field line, it slices towards the foul pole. And you could, I won't try to do it here, but you could go through an analysis, with what that direction of friction is. Balls hit this way are going to have a side spin like this, and balls hit that way are going to have a side spin like that. It always takes it towards the foul pole. And that's a very familiar result. You see that all the time when you watch a game. Top spin gives rise to tricky bounces in the infield. Again, and how does the batter put top spin on the ball? The batter puts top spin on the ball by hitting above the center of the ball. And then the frictional force is acting, let me get it right here. Okay, the frictional force is acting in this direction, which sets the ball spinning with topspin. The batter hits below the center of the ball to put backspin on the ball. Again, the same reason. Backspin keeps the balls in the air longer. You see that. Tricky pop-ups to the infield. Okay, so here is looking at some trajectories, some typical trajectories as a function of the offset between the ball and the bat, that vertical offset. So here the ball is always hitting under, always hitting at least under. I'll tell you what this is all about in a second. Always hitting under. Okay, so here is a head-on, so it's a line drive. This is something that probably ends up being a pretty good hit. You probably get a single on this. You hit it a little bit lower. This is a 1/4 inch below center, and it takes off at a bigger angle. It travels quite a ways, 1/2 inch. 3/4 of an inch, but now you start to undercut too much and it's starting to look more like a pop-up. And then you could have all sorts of funny trajectories. Look at this one here. There's sort of a cusp. And look at this one here. Actually, I taught a course a few years ago, and in my course was a student who had been a catcher in high school, and he verified that this is actually what happens. So what's going on here is that on the way up, the ball is going roughly straight up. It's got a lot of backspin on it because you've really undercut it. Lots and lots of backspin. So what's the direction of the Magnus force on the way up? It's back this way. And then it slows down, it stops, it comes back down. Now the leading edge is down here. The Magnus force is the other way. So catchers are taught, I've been told, don't overcommit on a pop-up behind home plate. Wait till it starts to come down and then commit yourself because it's going to do something like that. But I have a nifty little video, and this will be the last thing I show you. Yeah. Well, I've been somewhat anonymous, I have to say. They don't know it's me. No, actually, when I go and look at what people are saying about it, I think people are quite happy with that. I mean, some of the coaches are not happy, but I think most of them they are. That's what I've been reading anyway. Well, why does the NCAA regulate bats to begin with? I'll give you 2 reasons. One reason is they're worried about injuries to pitchers and corner infielders because the ball's coming off the bat so fast. But that's maybe not the primary reason. Primary reason is to restore the game to the traditional balance between pitcher and batter, which had really gotten out of hand. And it's a long, long story, but back in 1997, the final game of the College World Series read like a football score, like 19-17, and fly balls were going out of the park at a big rate. Then they instituted regulations, and slowly the statistics started to decrease again. And then in more recent years, the last few years, there are these new types of bats, not aluminum, they're made of carbon fibers, composite materials, that have difficulties with I won't go into all that. And so the home runs started to rise again, and the NCAA really felt they needed to do something. So they took this action 2 years ago, and gave the manufacturers and the teams 2 years to get adjusted to the new rules. Yeah?
How about the baseball itself? How much changes have been in the manufacture of baseball, and how has that affected the outcome of the game?
That's a good question, and it's a question that comes up almost every year around this time of year. There's been a couple of weeks of Major League games, and people look at the statistics. Oh, did you see it? Okay. Well, it'll go back again. I'll get to your question in a second. Okay, watch this. Now, this is a pop-up. You see, he overcommitted, and look at how the ball bounced. You see how the ball bounced when it hit? Okay. Exactly how do you expect it to bounce if it had a lot of backspin on it? Okay. You can see it from here. You see it bounces backwards. Okay, anyway, that's what I wanted to show you. All right, well, let me just finish. I'm just about done, and then I'll get to your question. Final summary, physics of baseball is a fun application of basic and in some cases not so basic physics. You can check out my website if you want to know more. And back to one of the things I said at the beginning, I'm living proof. And just to prove it to you, this is me at the Red Sox fantasy camp 2 years ago, and didn't help me one single bit knowing all this. So thanks very much. Why don't you turn the light on? So since you've already asked the question, so the question is, what about the ball? Have there been changes in the baseball itself? So we know the baseball has this relatively low coefficient of restitution. A change in that coefficient of restitution will affect how the game is played. And there are people who suspect that the ball has changed, but there's no real evidence that it has. And the people who do the measurements, the quality control measurements, the Major League balls are made by Rawlings, and I actually talk with them regularly, and they tell me that they do careful checks, and they're within fairly tight specs. So, but this time of year, as I said, is when conspiracy theorists emerge from their grassy knolls, so to speak, and suspect that something is funny with the ball, because based on the first 2 weeks of data, the number of home runs has gone way up. But these are just statistical fluctuations that over the course of a season will average out generally. Yeah.
Can you talk briefly about the different, why ash is the popular wood for bats? Opposed to other wood?
Well, in fact, ash and maple are about 50-50 now. And why ash or why maple? I'm not an expert on these things. Partly it's the density, so you can build a bat of the right shape and not have it weigh or something reasonable. Partly it's strength. Partly it must have to do with the elastic modulus of the bat, how stiff it is for vibrations. So all those things somehow conspire to make ash a good wood for that. But partly because of Barry Bonds, who, when he broke his single-season home run record in 2001, he was using a maple bat. And he has now popularized the use of maple bats. And so now half of major leaguers are using maple bats. As far as I can tell, for no good reason. I can't figure out any reason why one would be better than the other. Yeah.
With all the information that you said is available on every pitch ball, why do we still have umpires calling balls and strikes?
Some people ask that question.
Automatically done that in tennis and completely
Yeah.
eliminated.
Okay, so with the kind of information that we have on tracking pitch balls, especially where they cross home plate, Why do we bother having a home plate umpire? Well, okay, look, I can't give you an answer. I mean, it wouldn't be baseball without a home plate umpire. There are people who spend a lot of time worrying about differences between what the umpire calls and what the system shows. The system is not without problems. There can be mistakes. So, and baseball, Major League Baseball is a very conservative sport in the sense that rule changes, come about on a very, very slow time scale. So you could probably bet the farm that Major League Baseball will never use non-wood bats, that they would never replace umpires with some automated system. Now, they have started to institute instant replays on certain types of batted balls, and that may end up growing a little bit, but probably not on certainly not on called balls and strikes. I don't believe it, that they would do that in my lifetime. Yeah, Carolyn.
I'm interested in the effect of drag. In Denver at Mile High with, say, less dense air and low humidity.
Yeah.
Versus,
That's the slide I skipped, actually. But okay, good. You had.
I mean, and if the Denver team plays half its games at home, and, is there any effect or correlation?
There's absolutely no question about it. And the golfers here must know also that when you play up here in Santa Fe versus playing down at sea level, there's you can hit the ball further. The air density in Denver is roughly 80% of sea level, and you could actually look at home run distances and how far a ball travels for given initial conditions, that sort of thing. And a ball travels maybe 25 feet further, roughly speaking, in Denver. That's a huge amount, by the way. Of course, they compensate a bit by having the fences further away. It's a very, Coors Field is a very spacious ballpark. So the fences are further away to partly compensate. And they have the humidor, which also partly compensates. I'm answering you. Yeah, it's a well-known effect, and it's a big effect. But by the way, it also affects pitch baseballs. So curved balls don't curve as much, and pitchers claim to see that effect. They claim roughly a pitcher, the break will be only roughly 80% of what it is at sea level. So, Jer?
What causes a knuckleball to do the crazy things?
I'm not sure I fully understand it, but I used to think that the stitches had a lot to do with it. But you told me just yesterday that you saw it on a smooth golf ball, a knuckling effect. Yeah. The conventional, there actually was a really great set of experiments done in a wind tunnel maybe 20 years ago, where you could measure the forces on a ball in the wind tunnel. The ball is sitting there and the wind is blowing over it and there are little force probes attached to it. And they tried measuring the force with different orientations of the ball relative to the seams, and you could really see big effects. You could almost see discontinuous effects depending on how close the seam is to the front of the ball. So what's supposed to happen is, again, I'm not an expert on it, so I'm just sort of telling you what they're telling me. When the air flows over some obstruction on the ball, like the seam, or some other obstruction, like a dimple on a golf ball, the airflow changes from being a laminar smooth flow to a turbulent flow, and that sets up little air currents, then the ball ends up breaking in that direction. And when I looked, I just showed you Tim Wakefield's knuckleball and how much it breaks, and you see it's breaking all over the place. And my interpretation of that is that what Wakefield does when he pitches the ball, there are slight little perturbations in the initial conditions, the initial orientation of the ball, and those slight changes actually gives rise to big effects in how much and what direction the ball actually moves. If you look at the tracking data on his pitches, it actually looks like a fairly smooth trajectory. It's just breaking in a direction. It isn't, so when I showed you Jon Lester, you saw there were these nice clusters, and you know, it's a big blob for a wake field. So it's sort of like a chaotic system. Small changes in the initial conditions give rise to big changes in the outcome. Yep.
So on Rivera's cutting ball breaks after 30 feet, is that just because the ball is slowing down as it's coming in? Is that what?
No, it's actually a continuous break. It's just, so when I show those two lines overlapping, they're not quite overlapping if you really, really look carefully. So the, the effect is even bigger than that. So the amount of break is proportional to the square of the time over which the force occurs. And so there's 4 times as much, you know, roughly 3/4 of the break occurs over the last half of the trajectory. Only 1/4 occurs over the first half of the trajectory. So it comes down to the batter being able to recognize small little differences. You know, one of the things, a slide that I didn't include in this talk was comparing a fastball with a curveball. And it's very hard to get those two pitches to look alike. Yet you see all the time batters swinging at a pitch that breaks down almost into the dirt. They were simply fooled. But because a fastball is thrown faster than a curveball, it's thrown with an initial slightly downward trajectory. A curveball is thrown either level or sometimes even with a slightly upward trajectory. So people always talk about the hump of the curveball. If you look at the initial part of the trajectory of a curveball, it's separate from a fastball because it's gone upward slightly, and then it comes down and catches up to it. And if a batter's not good at picking that up, if the hump is not too big, okay, and the batter can't pick that up, then the batter can simply think that that ball is a fastball, and it's going to, you know, come at a certain height, and the bottom seems to fall out of it at the last minute. It doesn't, of course. It's continuously breaking. Yeah.
Why is the humidor effect so large?
Why is the humidor effect so large? I actually just wrote, why is the humidor effect so large? Okay, so in Denver, the relative humidity, you know, typically is what, 30% for an early evening on a summer night. The coefficient of restitution of a baseball is humidity dependent. It's a long-term effect. You can't, it's not just the humidity, it depends on how it's stored. It takes a week maybe to come to equilibrium. But when the ball absorbs water, the coefficient of restitution decreases. So beginning with the 2002 season in Coors Field, they started storing the balls in a humidor at 50% relative humidity, 70 degrees Fahrenheit. And there was an immediate change in home run production. Immediate. I mean, and you could look at the data. I actually wrote a paper on this. I have a paper about this effect that's going to be in the American Journal of Physics. It'll come out, it's been accepted, it'll come out in another couple of months. And then I also wrote, for those of you who are baseball bloggers, I wrote an article for Baseball Prospectus, specifically looking at Coors Field and also Chase Field in Arizona, where the effect would even be bigger, because there the humidity is like 20%. And they're considering storing the balls in the humidor. So by storing the balls at 50%, the ball is less lively, and the number of home runs are going to go down. The ball's not going to be hit as hard. And when I calculated this effect, based on data that I had for the humidity dependence of the coefficient of restitution, as well as the weight of the ball, which is a smaller effect, but still you have to take it into account, and looking at home run data and everything, what happened was with the humidor in Coors Field, the home runs per game dropped by 25%. That's a pretty big number. I calculated, just based on these measurements, that it would be 29% or 28%. It was embarrassingly close. The calculation had no right to be as good as it was. Okay, but it came out pretty good. And if I extrapolate that to Chase Field in Arizona, it would be a 35 or close to 40% effect. Huge effect.
So in Boston, do you expect the home run rate to go up?
Good point. Yeah, the relative humidity in most ballparks is actually higher than 50%. So if you stored balls at 50%, the home run rate Averaged over all of Major League Baseball would probably go up. That's a good point. A point that I actually brought up in this little paper I wrote.
Is there any other really pressing questions? A lot out of time. So
What's your take as a physicist on the infamous pine tar incident?
Oh, yeah, the pine tar incident. Okay, who knows what the pine tar incident was? Some people know. George Brett, back in the 80s, sometime, he hit a home run, and then they inspected his bat. So, you know, batters put pine tar on the bat. I don't know why, to improve their grip or something. I don't know why they have to do it, because they all use batting gloves. It's part of the folklore of baseball. But maybe they weren't using batting gloves back then. It's possible they weren't. And there's a rule about how high on the bat you can put the pine tar. And he exceeded, you know, the pine tar went a little further than that. And the question is, did that affect the home run? The answer is almost surely not. Okay, almost surely not. There's already enough friction. So the only way it might have affected the batted ball was he might have been able to get a little bit more backspin because there's more friction. The point is, there's already enough friction to give you plenty of backspin, and more friction doesn't help you get more backspin. As long as the coefficient of friction exceeds a certain value, you're going to get plenty of backspin. So the home run was taken away, and then it was given back. Then it was, let's see, how did that work? The home run was taken away, and George Brett went ballistic. I mean, it's one of the great videos, baseball videos of all time, watching George Brett go ballistic. And then the commissioner reversed the decision, or the president of the American League, I don't remember which, and they actually had to go back and replay the game from that point. Yeah.
Okay, thank you very much.